New section, and this is about the greatest integer function. So let's see the definition. For any real number x, we denote by this symbol x enclosed within square brackets the largest integer less than or equal to x. And for every real number x, this of course exists. That is, this is that unique integer which is less than or equal to x, and because this is the largest one not exceeding x, so the next one, that is this plus 1, will exceed x. That means it will be strictly greater than x. Or in other words, we have these inequalities where this is just this and this one leads to this. X minus 1 is less than this greatest integer value. Now let's see some examples. So let's see these values. The greatest integer value of minus 3 divided by 2 is minus 2. That of square root of 2 is 1. That of 1 divided by 3 is 0. The greatest integer value of pi is 3, and that of minus pi is minus 4. Let us see how, say we pick 3 of these, say this one and this last one, and see exactly why these values are coming. It's better to see the things visually. Let us take this number minus 3 divided by 2 on the real line. Now this is how the integers are situated, or more accurately, this is where the point is situated which corresponds to minus 3 divided by 2 with respect to the integers. This real number lies between minus 1 and minus 2. Actually, if you write its decimal expansion, decimal representation, it is minus 1.5. It lies halfway between minus 1 and minus 2. Now we are seeking the greatest integer less than or equal to minus 3 divided by 2. Equality is not possible because this is itself not an integer. So we seek the greatest integer that is less than this. Now all the integers that are less than this lie to the left of this, and the greatest among them is minus 2, because the others minus 3, minus 4, they are smaller. The greatest one is minus 2, and that is why you are getting minus 2. So geometrically speaking, if you think of your real number x as lying somewhere on the real line, then you have to look on the left side of x, and there you see the nearest integer, that is the greatest integer value. If you take square root of 2, for example, it lies between 1 and 2. So the greatest integer value is 1. The greatest integer less than or equal to root 2. You have 1, 0, minus 1, and infinitely many others, all of which are less than root 2, but among them the greatest is 1. That is why you have 1 here. Similarly, you think of this minus pi. Minus pi is minus 3.14159. The point here is that it lies between minus 4 and minus 3. So the greatest integer value is minus 4. But if you think of pi similarly, pi lies between 3 and 4. So the immediate next one, if you look to the left of pi, is 3. So that is why this one is 3, but this one is minus 4. So you have to be a little careful with the sign. So these are some examples. And now next we see some easy observations that we can make immediately from the definition of greatest integer function itself. The first observation is this: for any real number x, there exists a real number theta between 0 and 1 in this manner, that is, theta is non-negative, it's greater than or equal to 0 and strictly less than 1, such that x equals its greatest integer value plus theta. We can actually demonstrate this observation also quite easily. So this is the demonstration. You express the given real number like this: adding and subtracting its greatest integer value. Now you already have these inequalities about the function, that the greatest integer value by definition is less than or equal to x, and it is strictly less than it, that is the greatest integer value plus 1. Now what you do, you subtract the greatest integer value of x throughout, so that this minus itself will be 0, that is less than or equal to x minus this, which is less than 1, and then you just take theta equal to this. So that way you derive this result. Result means it's just an observation, and there is one more. So this is that other observation: for any real number x, x equals its greatest integer value if and only if x is an integer. That is the only situation in which x will equal its greatest integer value. You think of why this is true. Okay, I am leaving this to you. Now next we have this important theorem, theorem 6.9. It says that, say n is a positive integer and p is prime, any positive integer and any prime, then the exponent of the highest power of p that would divide n factorial is this. You see that this is an infinite series, but actually this is a finite series because the terms eventually become 0. Let us closely look at the statement once more. What the statement says is that the largest or highest power of p, there will be a largest power of p which divides n factorial. What do we mean by that? There is a p to the power alpha, where alpha is some non-negative integer such that p to the power alpha divides n factorial, but the next higher power p to the power alpha plus 1 does not divide n factorial. Then alpha is the exponent of the largest power p to the power alpha which divides n factorial. The claim is that alpha is this. Now let us look at the terms of this series. Here we see the greatest integer function of what? Of n divided by p to the power k, where k varies from 1 to infinity. So the first term of this series is the greatest integer value of n divided by p. N itself may not be divisible by p, so that this ratio is not necessarily an integer. It is some real number, it's a rational number, but of course its greatest integer value will be an integer. Alright. And then the next term is the greatest integer value of n divided by p square. Then the next one is the greatest integer value of n divided by p cube. That's how the terms go. But of course, as k increases, the denominator increases, and eventually there comes a stage, no matter how large n is, there comes a stage when these powers of p with increasing exponent exceed n. They become greater than n. When that happens, this ratio becomes less than 1, and in that case, because at the same time it is positive also. Why is this ratio positive? That is because you are dividing a positive integer by another positive integer. So the ratio is greater than 0. But if this happens, then it also becomes less than 1, and in that case obviously the ratio only, okay, not the greatest integer value, the ratio only lies between 0 and 1, and so the greatest integer value becomes 0, and the next higher terms continue to be 0. So that is why, in spite of how this looks, actually this is always a finite series. Now the proof of course is available in the text, so I urge you to go through the proof, and if you do not understand something, you write in the comment section below. Now next we are going to see an example in which we will use this result. So this is example 6.2. Suppose we want the number of zeros with which the decimal expansion of 50 factorial terminates. Obviously you cannot expect to be able to calculate 50 factorial actually, multiplying all the positive integers less than or equal to 50 and then seeing how many zeros are there at the end of the number. So instead we will use this result, but how? And this amounts to knowing the exponent of the largest power of 10 that divides 50 factorial. Let me give you a small example. Small example means for the sake of our better understanding. Suppose that 50 factorial ends with 3 zeros. If you do the calculation and express the number in decimal representation, say there are 3 zeros. We don't exactly know how many zeros there will be, but say there are 3 zeros. Then what is the largest power of 10 that divides 50 factorial? Obviously it's 10 cube. So if we can know that exponent, that 3, then we have the answer, because that is the number of zeros at the end of the number. But the problem is 10 is not a prime number, 10 is a composite number, and the result that we saw just now only gives us the largest exponent of a prime power that divides n factorial. So we can do the job by considering the two primes that are contained in 10, 2 and 5. So we considered the case where the prime is 2 and of course our n is 50. So this is that series that we saw in theorem 6-9. Why are only these 5 terms appearing? Let's see, okay. You see that the largest power of 2 here is 2 to the power 5, that means 32. What if we take the next term? Then it will be 32 times 2. I am talking about the denominator, which is 64. Because 64 is greater than 50, all the larger powers of 2, the terms involving them, all of them will be 0. So only these greatest integer values are really the non-zero terms in that series. And if you do the calculation, this is what you get. I am leaving these values to you. Why they are this much, that I am leaving to you. This one you can just simply see that it's 25, because 25 is an integer, so its greatest integer value is 25 itself. But then we have these other values as well, and the sum turns out to be 47. So by that theorem, this is the largest power of 2 that divides 50 factorial. The next larger power, 2 to the power 48, does not divide 50 factorial. And in this regard, I want to say something else also. We normally call this 48, for example, the power. That is not the power, that is the exponent. This entire thing, 2 to the power 48, is the power. That's why we say the power 2 to the power 47 divides 50 factorial. It's not that 47 is divided in 50 factorial, no. The power of 2, which is 2 to the power 47, divides 50 factorial, and in that power, the base is 2 and exponent is 47. But next we are also going to do a similar calculation for the prime 5. Next, for the prime 5, that series is even smaller. Smaller in the sense that the number of non-zero terms is only 2. That is because 5 is a large prime. Large means its powers grow more rapidly than the powers of 2 grow. This is 5, this is 25, the next one is 125, which exceeds 50, and so the other terms are 0 in that series. Now this turns out to be 12, and that is why again by this theorem, this is the largest power of 5 that divides 50 factorial, 5 to the power 12, but the next larger one, 5 to the power 13, does not divide 50 factorial. To put things simply, If you expand 50 factorial as the product of all the positive integers from 1 through 50, and then you see how many 2's there are, if you really do full factorization of everything, you will get 47 2's. Similarly, in that same factorization, you will get only 12 5's. So that is why you are only able to get 12 10's, not more than that. So that's why 10 to the power 12 divides 50 factorial, but 10 to the power 13 does not divide 50 factorial. And that is why if one really calculates 50 factorial, there will be 12 zeros at the end of it.